Welcome everyone. We have Professor Haim Weizmann today from, he's an associate professor in the Department of Civil Engineering and Engineering Mechanics at Columbia University. So he's going to give the seminar on computational fracture mechanics. So his research interests are in computational fracture mechanics with a special interest in extended finite element method, damage and phase field methods, multi-physics, multi-scale problems, and inverse optimization methods. He has been engaged in diverse applications ranging from small microscales, for example, high strain rates impact problems on metals, and all the way up to large macro scales, for example, the fracture of ice sheets in polar regions due to climate warming. Professor Weizmann obtained his bachelor and master's degree in aerospace engineering from Technion and a doctorate degree in civil engineering from RPI. He was a postdoctoral fellow at the Scientific Computing Research Center at RPI and at the Mechanical Engineering Department at Northwestern before he joined Columbia in 2008. Professor Weizmann is the recipient of the 2012 Department of Energy Early Career Award, the 2014 Leonardo da Vinci Award from the Engineering Mechanics Institute of ASC, and he's currently serving as an associate editor of the ASC Journal of Engineering Mechanics and has been the past chair of the ASC Engineering Mechanics Institute Computational Mechanics Committee. So he's an expert in computational fracture mechanics, and I will invite him to speak. So it's over to you, Professor Weizmann. Okay.
Thank you very much, Suparno and Samit, for inviting me to give this talk, and thank you for the attendees. I cannot see who's attending, so I'm just gonna present. I only see Suparno here. So let me share my screen, but before that, let me just mention the background that you see is Columbia University in New York City. I guess in better times than we have now. Hopefully these times will come back to us very quickly from where we are now. So let me share the screen with you. Suparno, can you see my screen?
Yeah, I can see.
Okay. Okay, so my presentation, thank you, Suparno, for the introduction. I'm going to talk about recent advances in fracture mechanics, especially things that we have done in my group. As you know, fracture mechanics can be modeled basically from two different perspectives. One can model exactly the fracture, as you see here on the right side, when we model perfectly the fracture and the discontinuities. This is examples are linear elastic fracture mechanics and cohesive zone models. Or we can model it using a smeared approach, such as damage mechanics, or here you see phase field methods, non-local methods, damage methods. Or on the other side, you can see XFEM formulation. And so each of those methods have pros and cons, right? And let me go very quickly over those. And then what I will do, I wanted to give this lecture and talk about each of those methods separately. So for example, if we talk about discrete fracture methods, such as extended finite element method and so on, those are well suited to represent discontinuities. If you have discontinuities and you need to capture those discontinuities exactly, those methods will be perfect for those cases. However, disadvantage is that one needs to track the crack path, and also one has to deal with element integration schemes. And in addition, it's very hard to model crack branching and coalescence. On the other hand, the other methods, such as continuum damage mechanics or phase field methods, basically in damage mechanics, we have a bunch of micro cracks that are being transformed into a kind of a homogeneous domain, and essentially it becomes just an internal variable in your finite element model. All right, so the advantage is here, it's very easy to implement in an FEM code. And it's well suited to capture if you have many micro cracks or voids and so on. But the disadvantages of this approach is that it doesn't resolve discontinuous features exactly. Sometimes those are very important. And also there are some numerical issues that are associated with that. For example, you need to solve a nonlinear problem, and there are issues of convergence and things like that. So in my presentation, I would like to talk about these two different classes of methods that we have worked on. And I will start first with the discrete formulation approach, and especially talk about brittle and quasi-brittle fracture using the extended finite element method that I've worked on that. So what is, first of all, the difference between extended and standard FEM? If you see on the left side, if we model a fracture using standard FEM, the fracture has to conform with the crack, right? And if the crack is propagating, one has to remesh all the time your domain, which becomes a burden. On the other hand, if you look at XFEM, the idea is different. The idea is that rather than following the geometry, one would introduce new enrichment functions, and those enrichment functions will create a discontinuity that would allow you to generate those cracks, right? So that's the general difference between them. And what XFEM allows you to do is it allows you to avoid completely the need for remeshing, right? And so you just introduce new enrichments in the right location, and that's how you can track the fracture. So XFEM originally was developed by Ted Belichko, the late Ted Belichko in the 1999. And if you see here, there are two cracks which are shown here. Those cracks are enriched with two sets of enrichments. First, you see the first term here, this is the displacement field. The first term here is just the standard FEM shape functions. But in addition, there are two additional terms. This one, H here, accounts for the heavy side enrichments, which are behind the crack tip. And the function here, F, accounts for the singularity at the crack tip and what happens exactly at the element where the tip is located. So you can see those functions here. They have the square root R term, where if you take a derivative of the displacement, you get the square root R singularity, which is very well known in fracture mechanics. Now, where are those functions coming from? Those functions are coming from essentially from analytical solution. Those are known as Williams solution, developed in 1957. And it turns out that those functions is actually a series. It's not just these four functions, but it's actually an infinite series of solution. And so the first idea that we came up with is why do people truncate these functions after only the square root R term? Why not just take higher order term? And so the first thing that we have done here is have taken not only the first or leading order term, but also the other terms in that series. And all of them have been augmented as additional degrees of freedom in your model. And so just to give you an example, if you take all these functions and not only the leading term, you can see here a mode 1 fracture, and the stress singularity is apparent here. There is an analytical solution to this problem, which is shown on this figure in black. And you can see that if you use a standard XFEM, which is denoted by red, it deviates slightly from analytical solution. But if you add higher order terms, you can automatically capture very accurately the stress field ahead of the crack. And what are the advantages of this? The advantage is that you can avoid completely all sorts of stress projection methods or stress smoothing methods. Just by incorporating these higher order terms, you automatically get the correct stress response. Right, so where does this lead us? So now let's talk about how we extract stress intensity factors, which are used to propagate cracks. Those are needed for crack propagation, right? So our idea was to refer back to Irwin integral, what is called Irwin integral. And Irwin said the following: if we have a crack, which is shown here, right? The energy that's being released by the crack due to propagation, this is what essentially we are trying to compute. There is a direct relation between strain energy release rates and stress intensity factors, right? And so what Irwin said is that in order to compute that, it's the same as propagating the crack by a certain amount and then applying work to close the crack back to its original position. So the work that is needed to close back the crack is essentially the energy that's being released from the crack, right? So essentially this Irwin integral is given by the following analytical terms, right? So we have, for example, G1 and G2, stress intensity factors. One should integrate and with the integral limits from 0 to delta L. Delta L is a very small distance ahead of the crack tip. You should integrate the stresses and the opening displacement behind the stresses, right? And in my opinion, what is nice about this Irwin integral is that it automatically decomposes the strain energy release rate into its mode 1 and mode 2, as opposed to J integral, for example, formulation that one has to do an extra step, use some auxiliary fields and so on in order to decompose it to stress intensity factors in each direction. However, it's interesting that this Irwin integral has not been employed in calculations before. And the reason is that we need to compute the stresses in this integral. And the stresses should be very close to the crack tip. And so if you are not using special techniques, you will get very bad stress fields ahead of the crack tip, right? And so the idea here is that since we can exactly nail very accurate stress fields, we can directly use Irwin integral in our formulation, right? And so this is what we have done here. And I'm gonna skip over some of the analytical steps, but essentially the idea is to use the Williams solution, right? Plug it into this integral, integrate it analytically on one hand. On the other hand, use finite element approximation of stresses and displacement field with enrichment, integrate that as well, and then have match the coefficient in terms of square root R, in terms of the leading orders of R, and that leads to the following final results. You are solving, the only thing you need to do is solve this linear system of equation, and automatically, without any post-processing, you can get expression for G1 and G2. These expression will depend on this coefficient D1 or D2, and these coefficients are functions of your enriched degrees of freedom. All of this is available to you once you solve this linear system, right? And so what I'm trying to say here that as opposed to J integral methods developed by Rice and which became extremely popular over the last few decades. In J integral method, one has to take a path independent loop around your crack and do some post-processing and decompose the stresses into mode 1 and mode 2. While in our case, if you use Irwin integral, you automatically get it once you solve your system. And so some of the advantages of this I will show in a second. Some results first. So if we consider a typical incline crack as shown here, so the plate is pulled. What I'm plotting here, there are 4 different graphs. In each graph, there are 2 curves, one for K1, one for K2. And this is corresponding to different alphas. The difference between each of the 4 graphs is the order of enrichment functions that we are taking in our analysis, right? So if we only consider the leading square root R term, you see that it kind of deviates from the exact solution. But as you go higher in your orders that you're taking, you automatically can recover the exact solution. And again, there's no need to do any projection or smoothing steps in this case. Another advantage of this method, I think, compared with J integral method, imagine the case that you have 2 cracks which are approaching each other. As the cracks approach each other, imagine that you are using J-integral method, and that means that your path-independent loop that you're taking should not cross any other singularities that you have in your domain. But if these two cracks are very close to each other, then the path that you're taking should be very small. Otherwise, you will cut through another discontinuity, which you cannot have. Right? So which means that as the cracks are approaching each other, your path independence becomes smaller and smaller. And so in this case, you are going to have not accurate solutions if you're using J-integral method. But here, since we are using Irwin formulation, the additional distance that we are taking goes to 0 essentially. And all of this is done analytically, the integration. Then it means that the two cracks can essentially touch each other, and you will still get very accurate results. You see here on this figure, as the crack is getting closer and closer, the maximum error that we get is in the order of 5%, which is pretty good without doing much in this case. Another example where there's advantage of this method over J-integral formulation is in a curved crack scenario. If you're using a J-integral formulation, especially the domain version of J-integral, it has been shown in the literature that if you have curvature or crack curving, then the actual domain version of J-integral diverges at some point, unless you introduce additional features there. But what I wanted to show here is that there's nothing to do with the Irwin integral formulation. Automatically, you can also capture curving cracks. And this just shows that the solution here gives you very good results. Another example where this method is useful is in the case of bimaterial interfaces. If you have interface, so you have two different materials shown here. One of them has, let's say, Young's modulus E1 and Poisson ratio E2, and the other one E2 and E2. Then there are several issues that arise in this problem. First of all, you have a strong discontinuity where the crack is, but also there is in the interface, there is a weak discontinuity that one has to consider. And so if we explore the analytical solution in this case, which is given by this function here, this is Mokashvili's analytical solution with complex numbers. We will see that we have a singularity of square root r, but in addition to this singularity, in bimaterial, as you get closer to the tip, you also have oscillating singularity. It means that the stress field will oscillate analytically, it will also oscillate as you get closer, right? So this introduces additional difficulties. And what we have done here is propose to use a special enrichment functions, which also take into account the two different materials. So it's basically, we call that material dependent enrichment functions in the case of bimaterial problems. Some example here include the following inclined crack with two different materials. One can use either confirming mesh along the interface, and this is our enrichment, or we can use a non-confirming mesh where we enrich the whole region with the same those shape functions. And if we compare the results to the literature in terms of stress intensity factors, we see that both confirming and non-confirming gives us very accurate results. Another example that what one can do with this method is basically employ it within cohesive zone formulation. In cohesive zone formulation, there is an additional traction separation law which are given on top of the crack. And so you can embed that into your extended finite element solution. And essentially, you can avoid the issue of standard cohesive zone models where those are mesh dependent. It will depend on the mesh. And sometimes people will enrich all the elements with the traction separation law because they don't know how the crack is going to propagate. Here, this is coupled together with XFEM, and so the propagation is can be done without any remeshing on the fly. So here I wanted to show you a recent work that we have done, where we have, in addition to cohesive zone models, we also develop a special arc length method to capture the issues that one may have. So for example, here we have this notch plate problem under loading. This is the XFEM system. And what I'm showing here is the force displacement behavior. If the crack, so as the crack is propagating, as you push at this point F, you see that there's an interesting phenomena. This phenomena is known as a snapback instability that happens in this type of problems. And if one will not have an arc length method associated or that helps solve this problem, what will happen is that once this point reaches a peak, it will just drop down to this point and will continue. So you will miss this entire snapback instability region. That's why you need the arc length method here. And then I guess a final example on this topic is that we have also extended the idea to model shells and plates. I'll just mention that in plates and shells, not only that you are enriching the displacement field, but also one has additional bending terms and moments. And so one has to not only enrich displacement, but also enrich those moments with the, and as I mentioned in our method, we use high order terms. And so that would lead to very accurate solution of shell type problems. Here you see shell which is under tension and shell which is under torsion. And this is our enrichment functions which are shown here. So with this, I will conclude the first section. I wanted to bring some of the papers that we have published on this topic and move on to the next type of system. Now, I would like to talk about dynamic fracture of metals, where we have used continuum type description or phase field formulation to model this problem. So let me start first with the well-known experiment in this field. This is known as the Kalthoff experiment. And what they observed, they took a steel plate with two notches and impacted that steel plate with different velocity of the impact, right? When they had a very small velocity, they observed a 70 degrees crack that are formed out of the notch tips. This is basically a brittle fracture behavior. If they increased and took a very high speed impact, they observed a completely different phenomena. They observed what is called the shear band, which I will discuss in detail soon, in a completely different direction. This is referred to as ductile fracture. And then if you take some intermediate strain rates, you will observe a combination of shear bending and cracks at the same time, right? So up to now, there are pretty much no models that can capture all these three different strain rates with a single model. And that's what we try to do here, is develop a model that will be able to capture both cracks and shear bands, which are two different types of localization problems. All right, so first let me start with what is a shear band. A shear band, if we start by looking at the experiment done by Danny Rietl from the Technion, we will see that there are kind of shear bands that are formed in a circular cylinder. And so those shear bands essentially go following the following stress strain curve. Initially, there are homogeneous deformation and nothing really happens. At the second stage, there is what is called onset of localization, where heat and plastic strain starts to accumulate at a certain location. And then at region 3, you have what is called shear collapse, stress collapse, or the formation of the shear band, where you have very high temperature at just at these localized bands, together with very large plastic deformation, right? So these problems typically arise due to impact, blast, and other phenomena. So just to illustrate how this looks like, suppose that you have this structure, this metal, and you are impacting this metal. Then what you observe is the following. I'm plotting here on the left side the plastic strain, and here there'll be a stress versus time curve. On the left side, you see that after a while that you have impact that, basically nothing really happened. Everything is nice and homogeneous. So this is stage one. Stage two, you will have an onset of localized behavior at this point. And then you keep impacting that. You see the two regions are kind of like sliding off or shearing one from another. But this is not a crack. This is just, this is a continuum here that has high plasticity and very high temperature effect, right? So this is the behavior of a shear band. Now, if we want to model shear bands and any other localization problem, then we should be aware that one can have mesh sensitivity, which means that if you refine your mesh and you take more elements, counterintuitively, it's not converging, but it's diverging. As you see here, in the softening region, you increase the number of elements, you're going to get different solution all the time, right? And so what this means is the model lacks a length scale that needed to regularize the system and create mesh insensitivity. Otherwise, your solution is not reliable and has no meaning. And so people have proposed different methods for the regularization. For example, people propose to use non-local plasticity, gradient plasticity, rate dependence, introducing rate dependence, and also coupling thermal diffusion with inelastic response. So we essentially take the last approach here. And so what we propose to do is the following. We have here the governing equations of the model. The first equation describes the momentum balance, sigma stresses, body forces, displacement, and density. Second equation describes the linear elastic relation. Here it's given in rate form. D is the rate of deformation, dP is the plastic part, and dt is the thermal part. Equation 3 describes the thermal or the energy equation, where we have T, kappa is the thermal conductivity, and here we have a term that comes from the plastic work. Sigma contracted with dP is essentially the plastic work that's being generated, where chi is known as the Taylor-Queeny parameter, which is the parameter that converts the heat into plastic work, or some of the work is not dissipated as heat, but goes back and drives this equation. And so the last equation here is the plastic constitutive law, or the flow rule. And so what I wanted to mention, most people, what they do in the literature, they assume that this term is zero, what they call adiabatic conditions. And this allows them to basically have all these equations, all these three equations solved at the Gauss point, right? And so you essentially have very simplified numerics here, because you just have these equations at the Gauss point and you're solving the standard momentum balance equation. The problem with this is that this is what we claim, is that eliminates the only regularizing term that you have in the system, right? And so if you do that, you're gonna end up with mesh sensitivity, right? So what we do is we don't eliminate the term. We keep this term in our model. Some of the other feature in this model, so as I mentioned, D is the rate of deformation. We use standard J2 plasticity with the flow rule, which are shown in this equation. This is a viscoplastic model. And what is interesting here is to know that there are two main terms which contributes to this flow rule. The first one that is shown here is a strain hardening term, and the other one is what is called temperature softening. Right, so these two terms, they kind of compete with each other. Initially, on the high strain rate, you will have strain hardening, but then at some point the temperature will kick in, become large, and then it will create a softening. So that's what we have in this model. This specific model is called the modified Litonsky model in the literature. And the way we solve it, again, as opposed to many of the work that is in the literature, we solve it implicitly, meaning that we we first discretize the system using mixed finite element formulation, where we have degrees of freedom of displacement, stress, temperature, and plastic strain. And then every time step, we solve a nonlinear Newton equation until convergence, and then we move on with time. So just to show you that this model works, if I take a standard benchmark problem of a plate under different rates in tension, in this case, just one rate under tension, and I'm only considering the upper right corner. And if we take different meshes, one mesh is stretched in this direction, the other mesh is stretched in the other direction, and we plot what is happening along the diagonal, right? We will see that no matter what mesh you're using, the equivalent plastic strain exactly falls on the same curves, right? So basically, this is a proof that the problem is mesh independent, which is important. Another result here is a stress strain curve. The left figure shows our method incorporating thermal conductivity. The other method shows what happens if you're considering adiabatic condition, or kappa is equal to 0, you get this mesh sensitivity back. Right, so this term is very critical, and we need to keep it. Now, why is this term works? This is just a little explanation. If we go back to this equation, the energy equation, and we want to plot these two terms. One is the thermal diffusion term, right? And the other one is the source term, what contributes to the temperature, right? And we plot that for two different strain rates. Right? The blue lines will be the source terms, and the green line will be the diffusive term. And under two different strain rates, what we see is that these two terms are opposite to each other, right? And they are different at different strain rates. So this is the competition that creates a length scale between them, right? So if you add the two together, there'll be a length scale that is created, and this length scale provide a regularization in this case. I called it weak length scale because you cannot determine what is the length scale, right? It comes automatically from this model. These are the two terms. Right, so now I want to, in addition, introduce fracture, right? So far I just talked about strain localization. Now I want to talk about introducing fracture in addition. And so the idea is as follows. This is an experiment that shows that under penetration of this projectile, one will have both cracks and shear bands at the same time. And so how do we incorporate cracks in addition to this model? We have decided to basically introduce a phase field formulation into this model. So first, let me kind of very briefly mention what is a phase field method. Phase field method, I view it as basically part of continuum damage mechanics, but a very specialized continuum damage mechanics formulation. Essentially, it says that if you have a discrete crack, one can approximate that discrete crack by introducing some thickness to this crack, or some width to this crack. This thickness will be defined by this 2L0. And then you can basically have an internal variable called C in this case, or phase field internal variable, that will measure if there is damages in this point or no damage, right? And so originally this method was designed to basically approximate fracture mechanics. And so if we consider a standard discrete crack theory or Griffith theory, we will see that the total Helmholtz free energy in this model is what is stored, or the strain energy that's stored in the system, plus the surface energy, and this is the strain energy release rate that I talked about previously, before. So now with this approach, with this phase field or smeared approach, we will have an approximation. We will say that this model, this will describe now the strain energy in the system, which will be related to this degradation function, MC. And then another interesting observation here is that the discrete crack approximation previously defined over a surface, now it's going to become a volume integral and going to be approximated by this phase field parameter, right? So this is the essence or what is the idea behind this phase field model. Now for brittle fracture, one can approach it from a variational point of view, meaning that you can write a potential energy and minimize it, and the minimization would lead to approximation of fracture. But when you have plasticity and coupled physics, this cannot be done in this way. And one has to approach the derivation from a thermodynamic point of view, which is what I've done in my papers. And so at the end of the day, what you need for a phase field method, you need basically two parameters. One is the length scale parameter, how much the crack is spread over a certain distance. This is defined by L0. And you need to define the energy release rate. In addition, you need to say how are you going to degrade your element at certain point where you have a crack. This is called the degradation function. In addition, you need to know how the crack is evolving. And so one will use here different types. For example, you will split your energy into either spectral decomposition or volumetric deviatoric type. And in addition, one would require additional degrees of freedom to be added to your model. Right, so for elastic brittle fracture, now in order to introduce phase field, this is now you need to solve a coupled set of equations. The first one is just the standard equilibrium problem. And then the second one is the phase field evolution equation that comprises again of two terms, the diffusive term described here by this Laplacian and the length scale L0, and the source term which drives the fracture and propagates that. So before I go back to the dynamic fracture problem, I wanted to show some of the things that we have done in my group with phase field method, and then I will go back to talk about the dynamic fracture problem. So the first example here is application of phase field to hyperelasticity, and use that to model the behavior under large stretches of material. So for example, here you can see randomly distributed void in hyperelastic materials. And in this case, you will see inclusions, randomly distributed inclusions. As you load the structure, the difference is that in brittle fracture, if you have notches, typically fracture will initiate at the notches, while here fracture may initiate in arbitrary location as well. So this just shows that under different types of stretches, how the fracture is going to evolve in these cases. This is example one. Example two is recent work on viscoelasticity, viscoelastic material. Viscoelastic material describe many things. In this case, for example, we consider asphalt behavior, but one can also use polymers to describe viscoelasticity and so on. In viscoelasticity, one has to account for both creep and relaxation effects. And what you see here is basically an example where we have loaded a viscoelastic material. If there is no damage, then this circle will continue to basically coincide with the loading. But and the energy under here described hysteresis essentially. But since we are cycling the system with increased amplitude, then damage is created, and essentially this ellipse, you can find it in this paper, will shrink and rotate at the same time due to this effect. So here is just a 3D application, 3D point bending, and you can see how the fracture propagates to the load. And this shows that in order to solve this problem, because it's computationally intensive, it had to be implemented on a parallel machine. And final example, before I go back to my dynamic fracture problem, is a recent work on modeling fracture of bones. So we had a donor that donated his bone. This is the humerus bone. It's the arm, the bone in the arm here. And so the idea here is to study what happens if you load the bone and you get fracture, and essentially can we reproduce the same behavior as in the experiments. So from this, we have to use CT scan to model the bone, then translate that to finite element with some empirical laws that would take let's say the CT scan tomography and translate it into Young's modulus and elasticity. So you can see here how we generated the mesh. You can see here the cortical bone and the trabecular bone in the finite element model. And then we ran the phase field method and obtained the same fracture behavior as in the experiment. I'll just mention to those who are interested here, if we just use the standard phase field method, that would not give us the correct results. But since here every point has a different Young's modulus, so basically this is a non-homogeneous material, the bone, then we postulated that GC should also be changing at every point with the Young's modulus, and that led to the correct result at the end. Okay, so now let me go back to the system of equation that I talked about, the dynamic fracture model. And you can see that now this model, we have introduced additional equation, the phase field equation now introduced into this model, right? And so now we have these 5 PDE set that we need to solve in order to get both shear bands and fracture. Now note that we have a weak length scale here, denoted by kappa. We have a strong length scale denoted by L0. And other unique features in this model is that we have the Taylor-Queeny, a function of strain rate. And we also introduced here a new term, P plus, we call it, that this basically accounts for the plastic work that would contribute to fracture as well. If you don't have this term, then the material may not fracture at all, right? So this is a very critical term to introduce here. And these are some of the other derivation of the physics that's included. For example, we use a Johnson-Cook model here. We consider a cubic degradation function in general. And that's basically the critical points here. So now if we go to the implementation, we will have, again, a mixed finite element formulation. At every node, we will have displacement, phase field, and temperature degrees of freedom, while at Gauss point, we will have stress and plastic strain degrees of freedom. The system is solved implicitly and integrated using Newmark method, where at every time step, there are nonlinear iterations that are solved in order to converge and move on to the next problem. So let me show some example first. Here is a problem where we have an impact into this notch plate, similar to the Kalthoff problem that I showed at the beginning. And now we are impacting this plate at different velocities, right? And so what we want to see is that this model is able to recover the different failure modes by only changing the impact rate onto that structure. So if I zoom into the crack tip, on the left side, I'm going to plot the phase field value. On the right side, I'm going to plot the plastic strain, the equivalent plastic strain value. And I'm going to start with the 10 meter per second impact projectile, right? So here we are impacting at this speed. We see no failure mode. We see no shear localization. Phase field is small and plasticity is very small. If we increase the velocity, we suddenly see that there is a brittle fracture that is formed. in the phase field, so modal failure is fracture, but there is no localization, no plastic localization in this case. Increasing further the speed to 20 meters per second, suddenly we see a combination of brittle fracture and strain localization at the other part of the tip. And then, interestingly enough, increasing further the speed of the projectile, suddenly the brittle fracture disappears, and the only mode of fracture is a shear banding fracture. So in this case, we have strain, localized strain and plasticity, but no brittle fracture, which essentially suggests that this model can, I would not say can reproduce, but has the potential to reproduce these complex failure modes. This is just a summary of the different strain rates. So this is low strain rate, intermediate, and high strain rate. You see the meshes here, and you see the behavior in terms of phase field and plasticity. And here I have just an illustration of the first case of brittle fracture. If I run that example and impact this plate, you see fracture initiated at the tip and just propagated through the plate to create this brittle fracture. So now I'm coming to another question that I want to introduce here. The question I want to introduce is the following, right? I'm coming back to this term, right, which I claim is very important term. It's the thermal diffusion term. But let's see what this term is doing if we look more closely. Right, so we will take this example. We have a mode 1 fracture, but in addition to this mode 1 with mechanical loads, we will introduce a temperature gradient on its boundary. And what we will observe is the following, right? We will observe that there is a phase field or fracture that is being formed. And if I plot the phase field along this line AB, I'll see that, yeah, initially there was a small fracture and then there is a localization. So far, so good. But now let's look at the thermal response of this model. Right? If I plot along the same line AB, what is happening with the temperature? I see that no matter how time goes by, even though there is a fracture, the temperature gradient along this line remains the same. Right? It doesn't change if I have a crack. That means that it's indifferent to the crack. Doesn't care that you have a crack or not. In the same fashion, if we look at the fluxes, how they flow inside that plate. So in the initial stage, where there is no crack, the fluxes looks like this. But then when the crack is formed, the fluxes do not change, right? So again, the fluxes, the heat is flowing through the crack, which is obviously is not physical, right? So that means that something is not good in this model and something needs to be updated. And what we are proposing to do is basically say that the thermal conductivity has to degrade with the fracture that I have somehow. But how to derive this model, and probably there are many ways or several ways how to do that, we chose one approach that I would like to show here today. So our approach to derive how the thermal degradation, how the thermal conductivity degrades with phase field is based on, is inspired by Maxwell approach. This is basically a micromechanics type formulation that you can think of. So imagine that all this bubble or this sphere is a single Gauss point that you are sitting and you're zooming into this Gauss point, right? What we define is the following two problems, right? In the first problem, we will have that sphere with a void in the center of the sphere. And on the other hand, we'll define another problem with a full problem where we basically want to find what is the effective thermal diffusion in this other sphere, right? So this sphere, this void is going to be growing. And then based on this, how this void is going to grow, this is how we're going to find what will be our effective thermal conductivity. So in some sense, this is kind of a homogenization problem, which is solved analytically. How do we do that? So the first problem is defined by Laplace's equation with the temperature boundary condition on the outer sphere and flux boundary condition, insulated boundary condition on the inner sphere, right? And the other problem is defined in a similar fashion, but there's no inner sphere in this case, right? And so how do we postulate this problem? First of all, notice that this problem to Laplace equation has analytical solution in spherical coordinates, which are shown here. And this is what's called spherical harmonics. So these are infinite series, which has some cosine and exponent function, and those are the spherical harmonics analytical solution to this problem. Right? So our idea would be to correlate these two problems by minimizing the flux at the boundary, the inner boundary. And this we can do analytically because we have those spherical harmonics solution. All right, so going over these steps, first we define the error functions. This error function is going to have the spherical harmonics and some coefficients. Then we will use Parseval's theorem for spherical harmonics to define this the error that we have. In addition, there is another step that we will define damage here as the ratio of the area, voided area, versus the sphere itself. This will be our damage. And then finally, we end up analytically with the following term, which is the relation between kappa bar, the homogeneous solution, with the kappa of the original problem. This essentially defines a new degradation function that is now based on D, based on the damage. Right, so to make use of this idea, first thing, we need to correlate damage with phase field, right? Damage is not phase field. It's slightly different than phase field. So first, from thermodynamic arguments, we can correlate damage D with phase field in the model. This is number one. Number two, we are going to choose what is called monochromatic wave condition, which means that all these coefficients drop except for the first one. This is the easiest solution. And so what we arrive at is the following relation, or the following degradation function, which now D is replaced with C. So we have a direct correlation. This is essentially a family of methods, a family of degradation functions. And if we plot these degradation function as a function of the phase field, we will see that this function, all these functions, corresponds to all the curve here, right? So you take different ends and you get a family of different functions. But what is interesting to note here is that one uses the quadratic degradation function, the blue line, which is everybody kind of is very well known in phase field literature, right? This is a typical function. It means that it doesn't fall within the physical space of the newly derived function, which means that it has no physics. It has no physics basis, and the function doesn't fall within this micromechanics derivation. Right? So we argue that in order to degrade the thermal conductivity, we should use this function. So now let's see some of those results here. So we go back to our model and now introduce thermal conductivity to be a function of the phase field in addition. And we repeat exactly the same problem as we had before. Mode 1 fracture with thermal gradient. The phase field behavior is the same, but now let's look at the thermal response. So we see that if we plot the thermal response along the line AB, initially there is, before crack is formed, there is a temperature gradient, but then as the crack is formed, we see a discontinuity, a jump in the thermal response, as we would expect to have if we use discrete crack here, right? So that is more physical response than what we had before. If we now consider the fluxes will go in this direction as we had before. But now when the crack is formed, interestingly enough, the fluxes are rotating. So the flux field is aware that there is a crack here and now is rotating around the crack to capture that correct physics. So this basically described this idea. Now, to conclude, I just want to show a few other things. The first question that comes to mind, okay, this problem is very expensive. How do we solve this problem? And so here, I wanted to introduce another idea. So here I'm describing kind of the solvers that can be used to solve these coupled set of equations. And that would obviously increase the efficiency of this method, right? So first of all, we have black box solvers, right? Off-the-shelf solvers that one can use, such as LU or preconditioned GMRes type solvers, but these unfortunately are not very fast to converge, right? So what I wanted to introduce is another idea here, basically a new solver or a new preconditioning idea. The idea is to use what is called overlapping domain decomposition preconditioners that follow the physics as well, right? So how does this work? Imagine that we had here the shear band that is formed. We will define a domain here where the shear band is formed, and then we can have essentially two different domains in the problem, right? So basically, we will be aware of the physics that is formed, and so the idea would be to use an additive Schwartz decomposition where you can use different solvers in different domains. In the domain where something is happening, where the shear band or fracture is happening, we can use a very sophisticated solver such as an LU solver, and so factor the system at every time step and solve it exactly. However, where nothing happens, so basically in regions outside this domain, there's no need to use fancy solvers. We can use very light solvers, right? So for example, one idea would be use an LU decomposition, but only do the LU decomposition once in the elastic region, and just keep using it throughout the analysis, right? So this would significantly save a lot of time. So here are some examples. This is, for example, an example of a crack that is propagating, a shear band that is propagating, and this is the partitioning into processors. And here I'm showing some solution here where we have strong scaling and weak scaling solution. Problem size has reached to up to 4.5 million equations, and we have used 96 processors to show that our method shown in red behaves much better than, for example, or scales much better than an LU process or LU decomposition. Another example here is a weak scaling, which also shows that if you have the amount of work per each processors is the same, then the weak scaling of that system is also scales well. And then another way that my final slide, essentially, almost the final slide, is another way to effectively or efficiently treat the problem. And here I want to introduce my colleague Sundar Natarajan from IIT Madras, that is a collaborator on this work. And the idea here is that if we have a phase field that is propagating, rather than having a refined mesh everywhere, what one can do is have an adaptive refinement that would capture the propagation and more accurately. So an example here of this shear type problem is that you see a phase field here, and then as the crack is propagating, we have an adaptive refinement. Now, I would mention that adaptive refinement is a topic that many people have used before. Our idea here is to use what is called a stability criterion to find when to adaptively refine the mesh. And we have shown that this can be much more efficient than some of the other methods that exist. So with this, I think this is a set of publication if somebody is interested. I think with this, I've reached my conclusion. And basically, I just want to conclude by saying that I've shown that one can have, so basically there is no one problem that works for all, right? There are some problems that one can solve using discrete formulation. There are other problems that are better fit continuum formulation. It depends on the problem that you have. In particular, for me, I've derived a high order XFEM to solve brittle, quasi-brittle fracture and cohesive type fracture, but then use continuum formulation for hyperelasticity, viscoelasticity, bone fracture, and for this dynamic fracture problem. And basically, I think that there's much more to be done in fracture mechanics. So if there are some students listening to this lecture, I think this is a good topic to go into. So with this, I will conclude. Thank you very much for your attention.
Thank you, Professor Weitzman, for the very nice talk. So we will take questions now. I already have one question from Shailendra Joshi. So I'll just read out the question, and Professor Weisman, you can answer. Okay.
Okay.
From Shailendra Joshi, in the dynamic problem, wouldn't the wave speed provide a length scale? So.
Yeah, no, the length scale is not enough to provide a length scale. The problem is the wave speed. The problem is that the PDE system is not well defined. And so in order to have a length scale, one has to introduce that into the PDE equation. Otherwise, the only thing that will provide a length scale is H, is the element size. And actually the element size does depend on the wave speed, right? So in some convoluted way, it does provide a length scale, but it's not the correct length scale because you need to have you need to have this length scale not as a function of the discretization that you have in your model, but from a physical point of view. Hope I answered that question.
Okay. We have some questions from Professor Amar Chaudhuri. So he has 3 questions. I'll read them out. One is, what is weak length scale? So I think you discussed this somewhere.
Yeah, I can go back and can discuss it again. Let me go back. To the model. Right, so here I introduce. So basically I'm saying there are 2 length scales, right? The weak length scale is kappa, is the thermal conductivity. And the strong length scale is L0. Now why is this a weak length scale? And this one is a strong length scale? Because L0 is something that you choose, right? From the beginning, you say, okay, this is my length scale, and that's what I want to go. Kappa is a physical parameter. There's a thermal conductivity of the material, it's given. And now you can see also that these 2 equations are different because one is more of a rate type of equation and the other one is there's no rate here. So as I showed before, when we have thermal conductivity and we apply different rates, the length scale will essentially be different for the 2 different length scales, for the 2 different rates, as opposed to the phase field case that will always be a strong length scale, will be the same. That's what I mean by weak length scale.
Okay. So, so Amor has 2 more questions. So can you give some insights on the snapback behavior with curved crack?
Some insights of the snapback behavior.
Snapback behavior.
Okay, let me go back. Yeah, I think this is the snapback, right? So there are many. It turns out there are many problems in mechanics which have a snapback behavior, right? Sometimes you'll have a snap through instabilities. Sometimes you'll have a snapback instabilities. In the case of fracture, this type of behavior is very common. It depends on the thickness, for example, of this beam. And that would be something that would always, always will come in those type of problems. So in the snapback, the problem reaches a certain peak, and then there is, if you trace exactly the equilibrium path of this curve, you will see that it follows this type of behavior. But obviously, if we are using standard, let's say standard Newton method, right? A standard Newton method would not be able to capture this snapback behavior and walk on this equilibrium path, but rather it will drop immediately down here, and then you will kind of miss, you will kind of miss the snapback of the curve. So in order to capture that, one only has to use some sort of an arc length method to capture that.
Okay. And so another question from Amor is, what guideline can be followed to choose the degradation function in phase field method?
Right now, that's a very good point. Right now, the phase field method is derived from mathematical point of view, and the degradation function has to satisfy certain mathematical conditions, right? In order to make sure that the phase field parameter itself reaches 1 for example, and doesn't overshoot 1 as we can have in damage mechanics, right? So these degradation functions, typically, they are satisfying certain mathematical conditions. That's why, in my opinion, in that sense, damage mechanics is a more physical approach, because then you can calibrate your damage model directly to a behavior that one will have. But again, because of numerical issues, damage mechanics will have problems, right? And so one approach in damage mechanics would be to use what is called non-local damage models to address that. But from a phase field point of view, so for example, people have used in the literature either quadratic degradation function. Another very famous degradation function is called the cubic degradation function. And with cubic degradation function, people are trying to kind of match the linear elastic response of the material better in the sense that the quadratic one will curve or will bend very quickly, while the cubic one will go more straight, right, and reach a higher peak or a higher strength. So there are some famous papers that discuss it, but essentially, I think that the phase field comes from a mathematical point of view, essentially.
Okay. We have one from Srikant Vedantam. How different would your result be if you used a simple rule of mixtures thermal conductivity? So kappa C is kappa 0, 1 minus C, basically.
For the conductivities?
Yeah, for the thermal conductivity. So rule of mixtures thermal conductivity, how different would your results be?
So this is a good point, but the problem with this is that if sometimes I have damage that is, I don't know, 0.5. Right? So what would be exactly, you cannot directly correlate, let's say, the amount of damage with the amount of the thermal conductivity that you have. It's not a linear connection between them, right? It's a nonlinear kind of, you saw that the homogenization is kind of a nonlinear process. It's not just a simple linear ratio 1-to-1.
Okay. Also, Srikant Vedantam, should the LHS of phase field equation be dc dt? So I don't get this question actually. Should the left hand side?
I think they are asking if we should have a C dot in the equation. And basically, in the standard phase field for those type problems, C dot is not considered. Sometimes people would consider inertia, what's called micro inertia, where you have E double dot in the same equation. There are some papers that discuss that. Sometimes C dot will be added due to kind of numerical reasons. So basically to smooth the drop in the curve, you will add a C dot term in that equation. But in general, the most standard way is that C dot is not added.
Okay. So we have another question from Babak Ravaji. So do you consider diffusivity degradation? Do you consider diffusivity degradation occurs homogeneously, or degradation is a function of orientation?
So this is an excellent point. Actually, I did not present it here, but we have right now a paper under review which proposes to use, if I understand the question, proposes to use what's called non-isotropic or orthotropic degradation function. Because isotropic problem, basically the problem is that one has to satisfy Neumann condition and the crack tip. But isotropic degradation basically knocks down the diffusion in all directions, which is not over-satisfying Neumann boundary condition, right? And so anisotropic degradation function would make sure that the degradation only normal to the crack will be degraded, but the one that is tangential to the crack would remain untouched. So this is something that we have worked on and we're considering, and we show that indeed, if we want to recover better discrete formulation, we need to do anisotropic degradation function.
Okay. So we have from Sunwook Kun. When you use high orders from Williams expansion, doesn't it depend on geometry of specimen? I mean,
no.
Okay.
No, because the solution of Williams' problem is given only at the vicinity of a crack tip. That's the beauty of that solution. It doesn't depend on far loading and on boundary condition. It only depends on what happens in very close vicinity to the crack tip. But the solution itself is formalized in a kind of a semi-infinite domain, right? So you assume a very far stress field, and that's how they derive it. So that's why in all XFEM problems, it doesn't really matter. You are just taking what is happening at the crack tip itself. It doesn't matter what happens far away on the boundary conditions.
Okay. So from Professor Argodash, isn't the rate-dependent flow rule also contributes to length scale similar to Needleman type regularization?
So that's a good point, but it does supposed to contribute, and as was correctly mentioned, but unfortunately for this problem, it doesn't help so much, and something else has to be added here. So the viscous regularization doesn't help in this case. And that's why if you eliminate the thermal conductivity, as I've shown, and you do nothing else, you are getting mesh sensitivity all the time.
Okay. Okay. From Shubhashi Sarkar, cracks did not form at high strain rates. What is the physical interpretation? So that's the dynamic problem, I think.
So the physical interpretation is that crack should form, right? If you look at my original, I guess, Kalthoff experiment, that one, you will see that indeed cracks should form once the shear band are arrested. Or sometimes we have other problems. I didn't show it here. That will show that if you go back to the tension problem, you will have a shear band, and then this model will create a crack exactly on top of the shear band. And this makes sense because the shear bands are essentially a precursor to fracture at the end of the day. They act as a new. You can think of this problem, for example, the way I think of this is the shear band is creating a new notch, basically. And then the new notch, this is where the crack is going to start from the new notch. It's like a new concentration. So theoretically, I should be able to continue the simulation further and get the crack. But unfortunately, I stopped the simulation at that point and did not yet. This is something that's still on my list of things that I need to do to show that we have kind of the combination that crack will form after the shear band in this specific problem. But again, on the other problem with the 45 degrees shear band, the stretch, in those cases, I have shown that a crack will form exactly on top of the shear band.
Okay. Okay. So then we have, can you comment about how would you go in terms of adding crack nucleation into PF? Do you think that the stability criteria you mentioned can be used for that?
So first of all, PF, I mean, I guess the phase field method.
I think so. It's from Shmuel Ozufowski. So I think it's a phase field method.
So the nice thing about phase field is that, the nice thing about phase field method is that it already includes initiation, right? So basically the damage evolution law will automatically initiate the phase field at certain location. This is similar with damage mechanics, right? And so it's different than the discrete fracture where one has to introduce initiation of a crack. There you have an evolution equation in the phase field, and basically if the stress reaches a certain critical point, then it starts evolving there.
Yeah. Okay. And one final question I think we have from Dr. Himanshu Pathak. Kindly comment on higher order XFEM. How is it different from standard XFEM? Is enriched functions are different from standard XFEM?
Yeah, so I think I mentioned that. Yeah. Let me go back to the model. So these are the functions, right? So this is the slide that shows the Williams solution, right? And you can see that standard FEM basically is just F1. These are 4 branch functions that have a square root R singularity and have some trigonometric contribution. These are coming, if you plug in I equals 1 in the series, that's what you are going to get. All the square root R terms, right? So now what we are doing with the higher order terms, we are also taking R terms. We're taking R to the power of 3/2. We're taking R square terms, R in the power of 2 terms. So these are the additional F2, F3, F4 is the additional terms on top of standard XFEM that has been added here.
I have a question. Can I ask it?
Yeah,
I can't write it on the Q&A. I have actually 2 questions. One is for the hyperelastic material, when you use the phase field model there, is the formulation similar to the elastic case? Do you still go by the fact that there's a well-defined GC?
Yes, in that case, you go by the well-defined GC, but the formulation is going to follow some, they're going to be like a model, right? So either Neo-Hookean model, Aruda-Boyce model, Ogden model, different models for hyperelasticity that you can use. And then you're going to incorporate that. Maybe I will show, since you ask, maybe I'm going to show another thing here, if it's okay.
Yeah, sure.
I left it outside of this presentation, but I just wanted to mention on hyperelasticity. Let me find that. Okay, I think I have it here. Do you see that slide?
Yeah.
Okay, this is recent work that we have done. where we have basically 3D printed a polymer, and these are harder inclusions of the polymer, and this is a 3D printed material, right? And what we wanted to see, now this 3D printed material is basically treated as a hyperelastic material. In this case, for example, we calibrated the GC and the Neo-Hookean model that we used to the material that was used for the 3D printing. On the left side, you see basically what happens if we use the phase field method. On the right side, this is DIC, digital image correlation, that basically matches these two results. And the idea was to show what is the effect of the inclusions on the propagation of fracture, right? So model it with the validation to experiments. So you see, for example, this is just one case that I've shown here that shows that this is the experiment, this is the numerical model, that the fracture initiates in between inclusions. Because the inclusions are very close by to each other, the fracture would initiate there, and then propagate outwards. But if the inclusions are further away from each other, then it could be that the fracture would initiate at the notch, as I mentioned. Now, the GC, again, is calibrated for this specific material. The only place that I have seen with GC that is more kind of more difficult to handle is for the bone problem that I've shown. In the case of the bone problem, I have at every point, I have different Young's modulus. And so the question becomes, what should be GC for this bone problem? If we take a constant GC, then it means that, then I've shown that the crack path doesn't match the actual experiment in that case. And so what we have postulated that GC should be a function of space as well. So GC would change in your domain according to how the Young's modulus is changing in the domain. But this is something yet to be verified experimentally. I don't know how this can be done.
The other question is that in all these methods, fragmentation kind of problems where there's a lot of crack interactions and distributed cracking, that's still a computational challenge, right?
This is a computational challenge, but some people have worked on this, and they have shown that if you using phase field method, and then there's no issue, right? If I would use a discrete formulation for this problem, then I may be in trouble, right? Because then I'm going to have a lot of little cracks and a lot of XFEM, and it's going to be very hard to track all the fragments. But if you're using a continuum formulation for that problem, then I don't see any problems other than, yeah, computationally it will be expensive, but it will not be a problem to trace all the little fragments in this case.
Okay.
We have one final question from Nirmal Kumar. At high speed, shear band appears. Why not crack branching?
At high speed shear band, why not crack branching? No, this is what the experiment have shown. That's what we get. So we had models where we showed crack branching scenarios, but that did not include a shear band model in that case. So for these problems, we have tried to match the experiments, the Kalthoff experiment that I showed, and this is what the experiment is showing. I don't know why you don't have crack branching or fragmentation. I guess as the material becomes more brittle, maybe you will have more branching associated with that. But when you have metals and it undergoes a lot of plasticity, I would assume that shear bending is what is generated.
Okay. So we have no other questions. So thank you, Professor Weisman, again for the wonderful talk, and the attendees, the audience for attending it, and for the very interactive, questions that you asked. So
absolutely, it was my pleasure. Thank you for attending the lecture. I'm sorry I don't see anyone except you, Suparno, and Sumit. I don't know who is attending.
Yeah, thanks a lot. Thanks a lot for accepting our offer. It was a very nice talk. Yeah, thanks a lot.
All right.
Thank you.
Very good.
Yeah.
Okay.
All right. Have a good weekend. Bye-bye.
Okay. Bye-bye. 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 Bye. Okay. So I will switch it off, or Sumit, it will go to you.
Yeah, you can switch it off.
I can switch it off. Okay. Bye-bye, Professor Wiseman.
Bye.
Bye-bye. Bye-bye, guys.
Nice
Bye.
to see you.
Stay safe. Stay safe.
You too. You too. You too. You too.